All right, welcome everyone to This Explainer. I am literally so thrilled you're tuning in. Today, we are going to unpack something that pretty much everyone uses, but incredibly few people actually understand. We are diving into the unseen architectural magic behind the mobile internet. We're going to trace the exact miraculous journey of a single packet of data, from the device sitting right there in your hand, all the way to the cloud. It's a beautifully complex symphony, and honestly, by the end of this, you'll never look at your smartphone the same way again.
So let's just jump right in with a super simple question. When you tap a YouTube thumbnail on your screen, what actually happens in that split second before the video starts playing? We experience this instantaneous magic dozens of times a day, but the sheer amount of invisible engineering required to make it happen is absolutely staggering.
You know, this right here illustrates probably the biggest misconception we all have about mobile internet. Most of us just kind of picture a simple direct line, right? Your phone beams a signal into the air and boom, it magically hits Google or YouTube servers. But actually, the reality is way more complex. Your cell phone signal hits a tower, sure, but then it enters this massive, incredibly expensive, and highly complex piece of infrastructure called the mobile core. This hidden brain sits right between you and the public internet, acting as the ultimate gatekeeper and router.
To really wrap our heads around this, we're going to follow a single data packet's end-to-end journey. We'll hit the real mobile network, the wireless first mile, mobility and security, the mobile core brain, how we actually speed up the internet, and finally, we'll explain those super frustrating daily network problems.
All right, part 1, the wireless first mile. This is where we turn raw digital data into invisible airwaves.
So, right inside your phone, hidden behind the glass and the battery, there's a dedicated team of hardware working in literal microseconds. You've got the baseband modem processing the signal, the antenna physically broadcasting it, and your SIM or eSIM getting your digital identity ready. And all of this relies on radio frequencies, or RF, traveling over licensed spectrums.
The exact second you hit play on a video, that internal hardware translates your request into very specific electromagnetic wave frequencies. We're talking anywhere from 700 megahertz all the way up to 28 gigahertz for millimeter wave 5G. And here's something wild to think about. These specific frequency bands, they are definitely not free. Telecom companies shell out literally billions of dollars at government auctions just to secure the exclusive rights to use these invisible highway lanes in the sky. Crazy, right?
Okay, so once your phone broadcasts that signal, it hits the cell tower. But listen, a cell tower isn't just some giant dumb antenna. It's actually a highly intelligent aerial traffic cop. It is actively managing bandwidth between hundreds of users all at the exact same time. By using some pretty advanced spatial and frequency tricks, it might dynamically hand over 100 megabits per second to user A, who's downloading a massive file, while effortlessly dropping 20 megabits per second to user B, who's just scrolling through text. It is constantly prioritizing and dividing up the airwaves millisecond by millisecond.
Which brings us to Section 2, Mobility and Security, the unseen shield of the network.
Now, the whole point of a mobile network is, well, being mobile. Imagine you're on a high-speed bullet train, ripping along at 300 kilometers per hour, streaming a movie. Why doesn't it just constantly buffer? Well, it's all thanks to this miraculous process called handover. Telecom engineers meticulously map out cell tower coverage areas so their edges overlap perfectly. As your train hurtles forward, your phone and the network are just constantly chatting. In a fraction of a millisecond, the network seamlessly hands your connection off from one tower to the exact next one. Your movie never drops a single frame.
But hey, before any of that data is allowed to flow, you've got to pass the bouncer. Think of it like a digital turnstile. If you don't have a SIM card, the network basically sees you as an illegal intruder and drops you instantly. Your SIM card holds a unique identity number and a highly encrypted secret key. So before you can even load a web page, your phone uses those to mathematically prove its identity to the core network security servers. Once you're verified, you get the green light, and a securely encrypted end-to-end connection is established.
All right, connection verified. Next up, Section 3, the mobile core brain. Let's look at the actual architecture.
To really get how this core works, we have to look at a massive architectural shift. In older 4G networks, the control plane, which is basically the brain making routing decisions, and the user plane, the heavy muscle actually carrying your video data, they were tightly coupled together. They were stuck to each other. But in 5G, engineers did something brilliant. They completely decoupled them. Separating the brain from the muscle gives the 5G network this incredible agility to just instantly scale up based on traffic demands.
So looking at it visually, in that older 4G setup, data was forced down this rather clunky path through multiple decision-making nodes. 5G completely flips the script. The brain handles all the complex setup off to the side, which lets your actual video data bypass the bottleneck entirely and shoot straight from the cell tower directly into the core's user plane. It's essentially a streamlined, hyper-efficient digital superhighway.
And that highway leads right to this absolute beast of a machine, the UPF, or user plane function. Think of the UPF as the ultimate super router of the mobile network. It is doing an unbelievable amount of heavy lifting. We're talking translating network addresses, enforcing quality of service, and managing super complex routing protocols. The UPF is basically the final heavy-duty gatekeeper your data has to get past before it finally breaks out of the telecom's private network.
Which leads us perfectly into Section 4, speeding up the internet, or exactly why your video plays instantly.
The absolute second you request that video, a super fast 3-step sequence fires off behind the scenes. Step 1. The core network acts like a massive DHCP server, handing your phone an IP address. Step 2. A DNS lookup happens. It's basically asking the internet directory, hey, what's the exact IP address for YouTube? And step 3. The network routes your request over to the right server. But here's the real secret to modern internet speed. It almost never routes you to where you think it does.
Think about it. If you're sitting in Asia and you want to watch a video hosted on a US server, sending that signal thousands of miles across the Pacific Ocean and back, that introduces massive delay, or latency, and nobody wants to wait for buffering. So tech giants use CDNs, or content delivery networks. Your request actually takes a huge shortcut. It gets routed to a localized cache server sitting just a few miles from your house. You're getting instant speed because the data you're pulling is practically already sitting in your own backyard.
Okay, we've covered a ton of high-level theory. Let's ground this in reality with Section 5, explaining daily network problems. Why do things actually go wrong?
Well, it all comes back to basic physics. Earlier we talked about those invisible highway lanes in the sky, right? High-frequency waves like 5G's 28 GHz millimeter wave can carry massive amounts of data at totally blistering speeds, but the major trade-off is they have a very short wavelength, which means they have terrible physical penetration. Low-frequency waves, much slower, sure, but their long wavelengths let them easily punch straight through physical obstacles.
So, take the dreaded basement dead zone. Why do your bars instantly vanish underground? Because those high-frequency 5G waves literally just bounce off the dense concrete and metal of the building. The signal physically cannot penetrate to reach your phone. Now, on the flip side, imagine a packed New Year's Eve concert. You look at your phone, you have full bars, but absolutely nothing loads. Why? Because thousands of people are trying to squeeze their data through a super narrow 4G pipe at the exact same time. It's a massive digital traffic jam. The incredible speed of modern 5G comes from widening that highway massively, so all that concert traffic can actually flow freely.
So pulling this whole shebang together, we arrive at the ultimate end-to-end packet flow blueprint. It kicks off with the hardware and RF in your phone, the user equipment. It flies through the air to the radio access network, those dynamic cell towers handling handovers and traffic. It dips into the deep, secure routing brain of the core network, getting authenticated and pushed through the UPF. And finally, it merges right onto the IP backbone, fetching your data at lightning speed from a local CDN in the cloud. All of this happening in literal milliseconds every single time you tap your screen.
Which leaves me with one final thought for you. The next time you're on a train or standing in a crowd and you pull out your phone to casually connect to the world, will you be able to see this invisible blueprint? Will you appreciate the beautifully complex, multi-billion-dollar telecom symphony playing out right there in your pocket? Keep learning, stay curious, and thanks so much for joining me on this explainer.